With respect to curing methods, there are different ways in which we can cure concrete. Of course, ponding, spraying, fogging, these are all practiced in the field. There's also wet burlap curing that is often followed for vertical surfaces where it's difficult to really pond the moisture. Plastic sheet covering and insulating blankets are taken care of in regions where we have issues of low temperatures in ambient conditions, because of which there is difficulty in actually setting and hardening of the concrete. So, insulating blankets basically help in maintaining the temperature in the concrete, right. Plastic sheets are essential for highly flowable concrete which is susceptible to plastic shrinkage cracking. Now, this is something we will talk about later when we discuss high strength or self-compacting concrete. There is a high potential for plastic shrinkage cracking for exposed surfaces of high strength or self-compacting concrete. In such cases, it is beneficial to ensure that there is no evaporation from the top surface. So, plastic sheets are good. Steam curing obviously is used when we want a very high rate of strength development in the early stages, right. And we also do steam curing quite a bit in precast yards where we need to have an increase in the productivity of the production of the concrete. Membrane forming compounds is a subject that we will talk about in detail later on when we discuss the specific chemicals that are used as membrane forming compounds. Right. So, just to move on, we know that we have to cure concrete for attaining a specific level of strength. Now, how much do we cure it, right? The idea of curing, again, I think I had emphasized this previously also, is primarily to actually engage in concrete that is durable. Rather than strength, curing has to impart durability to the concrete, and that is where we really need to ensure that at least some level of strength has been ascertained in the concrete before we can stop curing. Typically 70% is the usual thought process. Now, what happens with 70% is that you have this for modern cements, the concrete strength at 70% is typically attained by about 7 days, and you will rarely see that in sites curing beyond 7 days is actually practiced. Now, you have certain circumstances in which concrete needs to be cured for much longer, and this can happen when you have concrete which has a very low water to cement ratio, where internal desiccation or self desiccation can be quite a realistic problem in the beginning. So, other aspects that you really need to worry about with respect to curing, the considerations for durability, not just attainment of strength, but also durability is important. The type and size of the structure. Usually for structures that are very large, the effect of lack of curing is not as critical as for structural elements which are very small. For instance, if you compare a beam to a dam, right, the effect of not curing on the beam is much greater than the effect of not curing on a dam. But that does not mean you do not cure larger structures, it is just that you cure them for a lesser duration. The type of cement obviously will dictate the rate at which your strength is being obtained. If you have a high early strength cement, then obviously you do not need to cure for too long. Ambient conditions in terms of temperature and humidity govern the rate of strength development. So, obviously they have an effect on the overall curing process. And use of accelerating and retarding admixtures, again because of the way that they affect the setting process. Sometimes it is factors other than these which can dictate the length of curing. Project scheduling, costs, people do not want to waste their time spraying water on concrete. So, it depends on who is at the site, whether curing is actually done or not. How long is curing done? Again depends on the whims and fancies of the people who are operating on site. And very often we see that curing is not really done for even 3 days, sometimes even 1 day. So, you really have a problem with respect to curing if you do not plan it well in advance, and if the project conditions demand such non-technical reasons sometimes to not do this process. Unfortunately, that is the truth, and that is what gets done in sites, and that really affects to a large extent the durability. It may not affect the strength that much. If you look at data for strength development in the laboratory, where cubes have been cast and possibly even stored in air dry atmosphere, you may still get about 80 to 90% of the strength without any problems. But when you really test the properties of the cover concrete, the durability is going to be significantly affected. Why? Because curing is obviously necessary to ensure that cement hydration gets completed, or rather at least progresses to the maximum potential. And what happens when hydration increases? Why is durability improved when hydration increases? What is the primary reason? What does durability depend on? We have talked about this. Durability depends on interconnectivity of the porosity, right? So, with more hydration, you are going to break that interconnectivity, and when you have less interconnectivity, you have less permeability. So, obviously, you have better durability. Okay. Now, cement setting time is measured in the lab using your YCAT apparatus, right? But the concrete setting time is not exactly the same as setting time of cement. Cement in concrete obviously undergoes hydration reactions, because of which it leads to setting, but the presence of aggregates and the environmental conditions wherever concrete is actually cast also have an effect on the setting process. So, you need to actually develop methodologies by which you can predict or at least measure the setting of cement and concrete on site. This is important from what perspective? Obviously, from the point of view of concreting operations, you need to ensure that you are finishing your surface of the concrete much before the initial set happens, because after that you really are not able to mold the concrete in the specific shape. Secondly, you want to know the final set, because beyond that point concrete dimensions are not going to change significantly. So, you can start removing the shutters which are on the sides, for instance. So, you have an obvious necessity for understanding the setting time of concrete from the perspective of planning your concrete operations. Okay. So, please remember, concrete setting time is different from cement setting time. Why do I say this? Why should concrete set at a different time than the cement? Oh, you are saying chemically the silica and the aggregates may affect the setting. But yeah, possibly, but less likely. How do you measure the setting time of cement? Sorry? Yeah, apparatus is fine. How do you make the cement or cement paste to determine the setting time? It is made with a certain water to cement ratio, right? You make it at your consistency level. In concrete, your water to cement ratio could be anything else also, depends on the strength of the concrete that you require. In concrete, more often than not, you will have chemical admixtures present. So, all these will definitely affect your setting time. Cement testing is supposed to be done at a controlled temperature and relative humidity. On site, concrete can be subjected to any kind of temperature humidity combination. So, there is no way that cement setting time can exactly predict what the concrete setting time is going to be. It all depends on the concrete mix that is used, and because of that you need to start measuring the concrete setting time, which can be done quite easily with the help of a penetration resistance device. So, you take fresh concrete that is supplied to the field, sieve it through a 4.75 mm sieve, extract the mortar component out, and just have these penetration needles that are actually inserted into the concrete at different time intervals to see the resistance to penetration of the concrete. So, as concrete sets, the resistance to penetration obviously increases. That is what you do in YCAT apparatus also, right? You are basically using a needle to penetrate the concrete, and you have an arbitrary checkpoint where you define that this much resistance to penetration is enough to call it initial set or final set. Right. So, now just let us briefly look at hardened concrete. It is not going to be a very detailed discussion, because it is quite simple to understand the basic properties of hardened concrete. The first and foremost characteristic is that concrete is excellent in compression, but poor in tension, right. So, we are really interested only in the compressive strength of the concrete. For all practical purposes, for reinforced concrete members which are subjected to any kind of tension, we believe that concrete in the tensile zone is, sorry? No, concrete is weak in tension, but how do we design reinforced concrete members like beams? There is no contribution to the tensile resistance by the concrete. We give all the contribution to the steel. So, in essence, concrete may as well be cracked in the tensile region, right. Now, obviously, if concrete is getting cracked, then we have to worry about crack widths. Depending on the environment of service, we have to ensure that we select enough steel to ensure that the concrete cracking does not open up too much. Why does steel have an effect on concrete crack opening? No, the cracks will allow penetration of external agents to corrode the reinforcement. But why is the steel controlling the crack width? No, how is the steel controlling the crack width in concrete? No, cracks are going to propagate in concrete as soon as the tensile capacity is exceeded. But the cracks are not going to open up because I have steel present. Why? No. So again, you're talking about all the reasons why we select steel as a reinforcement of concrete. But why does the presence of steel restrict the cracking in concrete? Sorry, perpendicular? Sorry? It's blunting the crack. Okay. But it may blunt the crack, but why does it control the crack opening? You've learned all this in reinforced concrete design. Think about it. Anyway. Now, there are several different factors that affect compressive strength. It's not just the water to cement ratio, although our fundamental principle of concrete design is based on the fact that strength is dependent on water to cement ratio. There are several other factors: cement content, type of aggregate, curing, age, ambient conditions, and incidentally even the specimen geometry can dictate the compressive strength. That is why we say that strength is not a material property. Then what kind of a property is it? We want to test the concrete as a material, and we say compressive strength is a performance parameter that we often call for in construction projects. So what happens? Why don't we say strength is a material property? What is a material property? Can you give me an example of a property of a material? A constitutive property? Sorry? Hardness, okay. But more easier than that, something which is coming intuitively to you before that? Modulus of elasticity, right? Elastic modulus, that's a material property. But strength is not. Why do I say that? If you test the strength, if you do a tensile and compressive strength of concrete, will you get the same modulus of elasticity? No, modulus is only defined up to the proportionality limit, right? So, will you get the same modulus if you do a tensile and compressive strength test on concrete? Yes, concrete has to have the same modulus, right, irrespective of the kind of test that you do on it. That is why we call it a material property, right. Strength on the other hand, as I said, it depends on so many factors including specimen geometry. So, you test a cube or a cylinder, you get different strengths. Why? Okay. Before that, of course, strength is also dependent a lot on the extent of compaction you can give to the concrete, and of course, that is determined by the extent of water to cement ratio that you have in your system. Depends on what kind of compaction you give, either mechanical compaction by vibration or hand compaction, you can get a different extent to which you can lower the water to cement ratio. So, technically the lower the water to cement ratio, the higher the strength, but there is a limit to it, because you cannot compact your specimen beyond a particular point, right. If you are, I do not know how many of you have actually made concrete in the lab and tried to compact it by hand, you will notice that if the concrete has a water to cement ratio less than about 0.4, you will not be able to compact by hand. So, at that limit, your strength will start going down because the degree of compaction will not be enough to completely avoid all the porosity in the system or voids in the system, right. But with machine compaction, with vibration, now we have roller compaction, vibratory rollers, all kinds of things are present. So, you can actually take the theoretical lower limit of water cement ratio down significantly, right. Of course, we have this law called Abram's law, named after the scientist who first talked about this law, which says that as the water cement ratio increases, the strength decreases. He proposed a power relationship, but it need not be always true of the concretes that you are testing. You can also have a linearly decreasing relationship. You can have a quadratically decreasing relationship. It doesn't really matter. Okay, this is some sort of a arbitrary relationship that is defined. You don't have to keep fitting curves between strength and water cement ratio using this Abram's law. It's just a statement that says that as water cement ratio increases, your strength decreases. Okay. Now, this water cement ratio is often called free water to cement ratio, which is the extent of water available in your concrete after you account for all the absorption by the aggregates. How much is the water absorption of natural aggregate typically? Like granite or limestone aggregate, what would be the extent of water absorption, you think? Ballpark figure? 5% would be too much. 1% or less typically, around 0.5 to 1% is more typical. Even less than that for coarse aggregate. For fine aggregate, you may have up to 1% if you have river sand. If you have crushed sand, if you make sand by crushing coarse aggregate, is the water absorption going to be higher or lower? If you use crushed granite or what we wrongly call as M sand, right, what would be the water absorption? Will it be higher or lower than river sand? Lower? Why? It will generally be higher because when you crush, you produce lot more fines in the system, and because of the silt size particles, the extent of water uptake by the sand can be significantly high. So, your water absorption typically, if you go to Mumbai for instance, your water absorption can be as high as 6 to 7%, which makes concrete very difficult to actually properly design unless you are doing water content measurements from time to time. So, it depends obviously on the extent of moisture absorption, which is dependent on the type of aggregate that you are using. Okay. Have a slide on this aspect about specimen geometry. You test a cube and you test a cylinder, you get different strengths. Why? Sorry? Cylinder? Slenderness. Oh, slenderness is only a problem if your length to diameter ratio increases significantly. No? What did you learn in structural engineering? At what L by D is slenderness a real problem? L by D should be more than slenderness 12, right, more than 12, but your specimen is only L by D of 2, right, 150 mm diameter typically is 300 mm height, 100 by 200. So, why does cylinder then produce lesser strength than concrete? You have a confinement effect of the end platens, right. You have the platens between which your specimen is getting loaded. If the specimen height or length of the specimen is not too much more than the width, then the confinement effect is felt throughout the length of the specimen, and that confines the specimen from bulging outwards and cracking. So, how does concrete fail when you compress? It bulges outwards and cracks, right. Rather than crushing, it bulges outwards and cracks, and that bulging outwards because of the tensile capacity in the lateral direction getting exceeded. So, when you have confinement because of the frictional effect of the platens, it restrains that bulging outwards, and because of which you end up with higher strength in cube, because L by D, effective L by D in a cube is 1, cylinder it is 2. So, because of that you do not get any pure compression in the cube, right. Anyway, so let us come back to now the tensile strength of concrete. Of course, it is only in some cases that we actually go and test the tensile strength. For instance, when we have concrete pavements, the flexural strength is often a performance parameter required to judge the performance of pavements, right. Rather than compressive strength, pavements, concrete pavements rely on the value of concrete flexural strength. So, it is important obviously to judge how the concrete is going to behave in flexure, and sometimes even the cracking potential needs to be judged. For instance, when you have a case of thermal expansion or contraction of the concrete, that is obviously going to lead to tensile stresses in the concrete. You want to know at what tensile stresses concrete failure is likely to occur, right. So, generally as a thumb rule, the tensile strength is around 1/10 of your compressive strength. When you test it in flexure, it is probably about 1/7. So, let us say you have a 30 megapascal concrete. In compression, the tensile strength will be, or flexural strength will be around 4 megapascal. If you do a split tension test, when you use a cylinder to test the split tension, you will get even lower strength than that, typically around 3 megapascals, right. So, we can use a direct tension, a split tension or a flexure test depending on the type of standard or type of specification that prescribes the choice of flexural strength. Direct tension is not that easy to perform because concrete specimens have to be at least 3 times the size of the aggregate. If you are using 20 mm aggregate, you should use at least a 60 to 75 mm size specimen. Such a specimen, if you try to grip at the ends, that may lead to a failure of the concrete by crushing at the ends rather than the tensile failure of the concrete itself. So, you may want to sometimes use a high bond strength epoxy at the ends to pull off the concrete, but if your epoxy is not strong, the failure will happen at the epoxy and you will not really have any failure in the concrete. The other thing to have a notch, but then again you are not testing a true flexural or sorry true tensile strength of the concrete, you are actually testing its the crack propagation ability. It is not exactly tensile strength, you have other factors at play there also, the sharpness of the notch and so on and so forth. Okay. Split tension is a very neat way to test tensile resistance of concrete. It is an indirect tension test because we are not really applying a tensile load, right, we are only applying a compressive load diametrically to the cylinder. And when we do a load application like this, the zone which is in most part of the cylinder or most part of the diameter is subjected to actually a constant tensile stress. And because of the kind of geometry we adopt and the line load that we give, we can actually test the tensile strength fairly easily, okay, using this equation 2p divided by pi L d. Flexural strength of course is done in 2 different modes, typically a midpoint loading or a third point loading mode. Sometimes it is called a 3-point or a 4-point test depending on where you are and what type of connotation they use for the different tests. So, 3-point or 4-point or midpoint or third point. Third point because this is exactly L by 3 and the all 3 distances are exactly L by 3. Right, what is the advantage of choosing the third point loading? What is the advantage of choosing third point loading? Yeah, you have a zone in the center where there is no shear, it is perfectly pure bending, right. So, you are actually getting a true flexural response of the concrete. So, when the first crack appears, you call it the modulus of rupture, MOR, okay. The flexural strength at the first crack is termed as modulus of rupture. How do you calculate the flexural strength? What is the bending formula, beam bending formula? M by I into Y, okay. So, M, let us say this is P by 2, what is M? Right, PL by 6 and Y is, if this is D by 2 and I is 1 by 12 BD cubed, right. So, what is this equal to? PL by BD square in the third point loading condition. In the midpoint loading condition, what is it? Okay, you can do this yourself, it is 3 by 2 PL by BD square. Does this mean that the strength in the midpoint loading test will be higher than the strength in the third point loading test? The formula works out to 3 by 2 PL by BD square in midpoint and PL by BD square in third point loading. So, does this mean that the strength in the two tests is different or modulus of rupture is different? It can't be, no. So, where are we going wrong? Sorry? Yeah, obviously. So, this is P1 and this is P2. You are getting the crack at different loads. So, depending on which way you do the test, you will get different loads, and when you do the calculation, you will get approximately a similar value for the modulus of rupture. Okay. There may be some differences because of the presence of some shear, because only exactly at the center here you do not have any shear. So, if your crack is exactly at the center, then you have a infinitesimally small zone of pure bending, otherwise you will have effect of shear also.